Hi, everyone. Thanks for coming to our presentation today, the MapTree, Recovering Multiple Solutions in the Space of Maps. This is a collaborative work with Simone Melzi, Max Safienkov, and Peter Wanka. Shape matching is an important problem in computer graphics, and it has a lot of applications, such as shape analysis, segmentation transfer, and so on. And the shapes we're dealing with, the discrete triangle meshes, such as the two humans shown here. Our goal is to find a pointwise map between the two triangle meshes, which means for each vertex on the source shape, we would like to find a semantically corresponding vertex on the target shape. The color shown here, they just visualize the correspondences between the two shapes. The color shown on the source shape uses the pullback of the color on the target shape. Simply speaking, if two vertices, they are corresponding to each other, they will have the same color. There are a lot of existing methods to compute a map between two shapes. For example, the point-based methods tries to minimize some energy defined on the points, such as the approximate preservation of geodesic distances. Another category of methods is parameterization-based, where the shapes are mapped into a canonical domain, such as a sphere, and the correspondences inside the canonical domain can be estimated. There are also some other methods try to use the optimal transport to formulate and relax the shape matching problem. Our work uses the functional map representation. This technique tries to find the correspondences between the functions defined on the shapes instead of finding the correspondences between vertices directly. In general, most of these methods, they try to propose an energy to define what a good map should be, such as they use the geodesic distortion or Dirichlet energy. And sometimes we also add the hard constraints to ask the pointwise map to satisfy, such as bijectivity. Take one of the most commonly used energy as an example, the geodesic distortion. It is defined as the difference between the geodesic distances between two vertices before and after mapping. If the difference is small for all pairs of vertices, we can say that the map is good, since the geodesic distance is well preserved after mapping. So a very natural solution to shape matching is just to minimize this energy of geodesic distortion to obtain a map. However, even though the geodesic distortion can well characterize a good map, it is very hard to minimize this energy directly. So for example, here on the left, we just show the landscape of the geodesic distortion on 10,000 maps. And on the right, we show the contour of the energy. So the map with small geodesic distortion are colored yellow, and the maps with high distortion, they are colored blue. So we can see that the map space is very complicated, and it has a lot of local minimum. And also the discrete nature of the pointwise map makes it harder to minimize the energy directly. There are some existing methods to try to address this issue as well. So for example, one method tried to find multiple candidates correspondences for vertex, and then select from the candidates to avoid global symmetry ambiguity. Another method discussed how to avoid symmetry flip during the map computation. So these methods, they can be helpful in some cases, but they do not make too much sense when multiple ground truths exist. So for example, let's take a look at the four valleys in the landscape. These are the four maps. They correspond to the local minima of the landscape. And we just visualize the four maps using color transfer. To better visualize the difference between the four maps, we visualize how the function shown on the source shape get mapped to the target shape. We can see that these four maps, they are just respectively a direct map, a symmetric map, and a back to front map, and a double flip map where the left is mapped to the right and also the front is mapped to the back. So all these maps, they are meaningful since they reflect the intrinsic symmetry of the given shape pair. In summary, we can observe that multiple ground truths can exist due to symmetry, and also the objective functions, such as the geodesic distortion we commonly used, they cannot disambiguate the differences between that caused by the symmetries. So therefore, in our paper, instead of avoiding symmetry flip during map computation, we try to find all meaningful maps and select the desired one later. And our method uses a functional map representation, and the map is encoded in the Laplacian basis. Here we show an example of a table. And we also visualize some eigenfunctions which are sorted according to the eigenvalues. As we mentioned before, functional map is used to map functions defined on the shapes. And in the discrete version, a functional map is a matrix that stores the corresponding coefficients between the corresponding eigenfunctions. For example, here, we show a 3x3 functional map that maps the first 3 eigenfunctions of a table to themselves. Here, in this functional map, we can see that the last diagonal entry is -1. It means that we would like to map the third eigenfunction of the table to the opposite of the third eigenfunction. This corresponds to a symmetry axis, as illustrated by the dashed green line. In this case, we can recover the corresponding pointwise map from this functional map, and we obtain a symmetric map where the red and also the blue legs, they are flipped. Here we show another functional map where the second diagonal entry is -1. It means that we would like to map the second eigenfunction gets mapped to its opposite. In this case, we get another symmetry axis, and the recovered pointwise map is shown here, where the yellow and the purple legs, they are flipped. This functional map is a bit more complicated, where we can say that the second eigenfunction mapped to the opposite of the third eigenfunction, and the third eigenfunction is mapped to the second eigenfunction. The recovered pointwise map is a rotational symmetric self-map, as visualized here. From the previous examples, we can see that the intrinsic symmetry information is encoded in the spectral domain of the shapes. And also the pointwise maps, it can be organized in the spectral domain along the frequencies. We can also use the Frobenius norm between two functional maps to approximate the distances between the two pointwise maps. This inspired us to explore the spectral domain to extract all meaningful maps. We therefore propose a method called MapTree to organize the pointwise maps into a tree structure. We use a compact functional map representation and expand the tree along the frequency domain. Specifically, we always start from the smallest functional map with size 1 by 1, which is fully determined by the first constant eigenfunctions of the given shapes. We then start to expand the functional map along the frequency domain, where we enumerate all possible mappings between eigenfunctions in a similar frequency. We only keep good and sufficiently different maps at each iteration. You can find more details about about how we decide which maps to discard or which maps to keep for further expansion. We continue the expansion until it reaches some termination condition. This allows us to extract multiple maps. For example, we can obtain 4 different maps, like they are different and also high quality between a human pair or between a human or a gorilla. We can also obtain 2 maps for animal shapes, such as cats, dogs, lions, and horses. We can also get more than 3 or 4 maps for man-made objects, such as table and glasses. As a comparison, almost all the previous work, they can only extract a single map during the computation. We also propose a better refinement method for shape matching, which is used in our MapTree algorithm. We improved the state-of-the-art refinement method, zoom out, which is proposed last year. This refinement method tries to enforce the orthogonality of a functional map by upsampling in the spectral domain. We follow a similar idea, but we try to enforce the bijectivity of the functional maps from both sides and try to enforce the orthogonality at the same time. Our bijective zoom out has a better accuracy with a similar computational complexity to the standard zoom out. In the following, I will show how our MapTree methods can be used for multi-solution shape matching, self-symmetry detection, and non-rigid shape matching. Here we show a pair of gorillas. Using our method, we obtain 4 different maps: a direct map, a symmetric map, a back-to-front map, and also a double flip map. Here we show 3 self-symmetric maps of a pair of glasses obtained using our method, which are a left to right map, an upside down map, and also a double flip map. Here we show a challenging case of a knot, where we can see that the state-of-the-art method for self-symmetry detection cannot work well in this case because the computed maps are just like broken. As a comparison, our methods can obtain multiple high-quality self-symmetric maps as shown here. Here we show another example of multi-solution shape matching, where for complicated input shape, we first detect its disconnected components. And for each of the components, we use our method to compute different self-symmetric maps. This can help us to understand the symmetry group of the original shape. Here we show a pair of human shapes from Shrike-Nighting dataset. We compare our method with existing refinement methods. In this example, we can see that the initial map has large symmetry ambiguity, where both arms of the target shape are mapped to the left arm of the source shape. In this case, it's very hard for the refinement methods to get a good map with a consistent global orientation. This suggests that it might be a good idea to compute multiple maps at the same time and select later if we prefer a specific orientation. Here is a quantitative evaluation of our method on Shrike-Nighting challenge with more than 400 shape pairs. Our method achieves the best accuracy and comparable smoothness compared to the state-of-the-art methods. We also propose an auto-selection algorithm to select the direct map from the multiple maps we obtained using our method, and this auto-selection is based on the cycle consistency. You can find more details in the paper. Here we show that our algorithm can also be applied to shapes with partial self-symmetry. In the middle, we visualize the obtained map, and on the right, we highlight the map on the partial symmetry regions. Our method is also robust with respect to mesh decimation. In the box, we show the source shape with around 5,000 vertices. And for a target with 7,000 vertices, we can obtain 4 different maps. We can then downsample the target shape to different number of vertices, such as 1,000, 500, 100, and even 50 vertices. We can see that our method can perform consistently well during the decimation. That's all. Thank you for your attention. And we have released our implementation, and you can find the demo code on GitHub.